Here we are at Multivariable Calculus, section 11.2 from your Edwards and Penny textbook, 3D vectors. Again, this is really just pre-calculus, but it's setting the stage for vector calculus later. Here we have three space, x, y, and z axes, and the coordinate, of course, has three components, x, y, and z. Now, if you rotate this space 90 degrees counterclockwise in the xy plane, and then 90 degrees counterclockwise in the yz plane, you get something that looks like this. It's the same space, but it's rotated. And some physics books draw it this way, so I just thought I'd let you see that. This way, your original piece of paper is like on the blackboard, and z is coming out towards you. Whereas in most math books we have x and y on a piece of paper lying flat, and then the z-axis coming upward out of the paper. Now, distance in 3D is very similar to distance in 2 dimensions. If you have 2 points in 3 dimensions, you can think of them as the corners of a rectangular prism, a box. And so the distance we want is the distance between those 2 corners. And we'll label those 2 points with subscripts. And first what we're going to do is we're going to look at L, which is the hypotenuse of the triangle on the face, the front face of this box. And its legs are the difference in the y coordinates and the difference in the z coordinates. So just using our old friend the Pythagorean theorem, we get L squared equals the difference in the y coordinates squared plus the difference in the z coordinates squared. Now, L and D, and that little side up there at the top left side of the box, form another right triangle because the red line segment is perpendicular to the front of the box and therefore perpendicular to L. So the red line segment and the green line segment are the legs, and then D is the hypotenuse. So now we have D squared equals L squared plus the difference in the x coordinates, and then we substitute for L squared, take the square root and put it in alphabetical order. And so it's sort of an extended Pythagorean theorem in 3 space. Likewise, the midpoint is similar. We just take the average of the 3 sets of coordinates to find the midpoint of a line segment. Now in 2 dimensions we have a circle, and we usually label the center HK, and if the radius is R, then here's our familiar equation for a circle. In 3 dimensions, again, this is really just based on the Pythagorean theorem, or the distance formula rather, because we're saying that the distance is all from the center to any point x, y is always r. So it's the same kind of thing with the sphere. We'll call the center HKL and the radius still r, and so the equation of the sphere just adds the z component the same way it did with the distance formula. Unit vectors. We looked at them in 2 dimensions. In 3 dimensions we have 3 of them, I along the parallel to the x-axis, j parallel to the y-axis, and k parallel to the z-axis, each 1 unit long, hence the name unit vectors. Now here we have a vector in 3 space, and it has 3 components. The point, if the vector is drawn in standard position with its tail on the origin, then the point ABC also names the vector, except that we use chevrons. Or we can think of it as the sum of 3 vectors. Here I have the vectors lined up with the dotted lines. If I scoot the vector AI over so that it's lined up with the x-axis, you can see that if you followed AI and then BJ and then CK, if you added those 3 vectors together geometrically, the resultant would be V. And so we can still write vector V in terms of ij and k this time in 3 dimensions. The dot product. Given vector A denoted that way and vector B denoted this way with the subscripts, turns out that A dot B, well, by definition, A dot B is the product of the first components plus the product of the second components plus the product of the third components. And notice that these are all numbers. So what you get when you dot 2 vectors is a real number, not a vector. Now there's another multiplication called the cross product, which we'll look at in the next section. And the cross product is a different way of multiplying vectors that creates a third vector. Now you might think, well, what good is the dot product? Well, here's a picture of A and B, two vectors in 3 space. And there's an angle between them, and it turns out that the dot product is equal to the length of the vectors times the cosine of that angle. And so the dot product is handy in finding the angle between two vectors. So let's show you why that's true, kind of briefly. Let's draw a third vector connecting A to B. And so that I don't have to keep typing in the absolute value, let's just let A, B, and C, without bold, be the lengths of the 3 vectors. And using the law of cosines, C squared, the length of C, is equal to A squared plus B squared minus 2AB cosine theta. Also notice that A plus C is equal to vector B, and therefore vector C is the difference between the 2 vectors if we just subtract vector A from both sides. And so the length of C is equivalent to the length of vector B minus vector A. And if we square both of them, then they're still equivalent. So using the components of vector B minus vector A, we can get C squared equal to the square of the individual components. So now we've got 2 expressions for C squared. And so on the next page, we're going to set those equal. Okay, so on the left, the length A, remember A and B were the lengths of vectors A and B, and so we can get those lengths squared by squaring the individual components. And then on the right side, I just multiplied those out, expanded them, and that looks pretty horrible except that lots of stuff cancels. Now we're going to divide by -2, and we get this. And then there on the right, you should recognize the dot product. And so rearranging it alphabetically, we have the equation that we wanted to show was true. Rearranging that, we can solve for cosine theta, and this is the form that's used mostly because we're usually using the dot product to find the angle between the 2 vectors. Now notice that if A dot B is 0, then that means cosine is 0, and therefore we have a right angle. And vice versa, if we have a right angle, then the dot product will be 0. Direction angles. Vector V forms 3 angles with the 3 axes. We're going to call the angle made with the x-axis alpha, and the one made with the y-axis beta, and the one made with the z-axis gamma. Recall our formula from the last example. And so to find alpha, we're going to dot V with I, and notice that we don't have to divide by the length of I because the length of I is 1. So we get a nice little easy formula. Likewise for beta, we're going to dot with J, and for gamma, we're going to dot with K. Projections. Let's say we have a light shining perpendicular to that blue vector. Then basically there's a projection of the red vector onto the blue vector, like a shadow. And that's what it's called, the projection of A onto B. Now let's say the angle there is theta. Then just using simple trigonometry, the length of that shadow is the length of A times the cosine of theta, because it's the adjacent leg of that triangle. And so the projection of A onto B, notice the B is the subscript here. It's read projection of A onto B. Then is that length times multiplied times vector B. And if you just look at the length of it, that's called the component of vector A onto B. And if you divide, this is kind of weird, but watch what happens. If you divide and multiply that quantity by the length of vector B, you get the dot product in the numerator. So now we've got a shortcut formula to find the component if you need a projection for some reason. And finally, work. Remember, work is force times distance. In vectors, it's the dot product because work is numerical, it's not a vector. So for example, here we have a little boy pulling a sled, and the vector shows the way he's pulling it. And then this vector shows the way he's walking. And let's put some numbers to this. Let's say the kid is pulling with a force of 25 pounds at an angle of 45 degrees, and travels 1 mile. How much work does he do? 25 for the force vector, 45-degree angle, and now he's going to go 5,280 feet. Because remember, work, we usually use foot-pounds, so change the mile into feet. Now, vector F is the cosine times I. If we change this into a sum of the two perpendicular vectors I and j, then the I vector component would be multiplied by 25 cosine 45, and the j component would be 25 sine 45 degrees. And then the distance is just along our x-axis. This is two-dimensional, not three-dimensional actually, although the formula works for 2 and 3-dimensional problems. So then the distance vector is just 5280 times I. So we dot those two together, and notice that the j component of d is just 0. And we get approximately 93,338 foot-pounds. Here's number 6. I'm going to kind of mix up the notation. We have IJK notation, we have chevron notation, we have letters with arrows over them versus bold letters, both describing vectors. So 2a plus b, you double the components of a, which makes it 2, negative 4, 6, and add to that the components of b, 1, 3, negative 2, to get the answer. 3a minus 4b, you triple the components of a, quadruple the components of b, and then subtract carefully. A dot b, you multiply the components together and then add those products. The length of vector a minus vector b, first you subtract the components and then you square those results under the radical using the extended Pythagorean theorem. And then simplify the square root of 50 to 5 root 2. And finally, vector a divided by the length of a. Well, we already did we do the length of a? No, we didn't, did we? So you take vector a and you divide by the square root of the components squared, and that comes out to 1/14. And then if you like, you can rewrite it in the IJK notation or just leave it alone. Example number 12. Find the angle between these two vectors in problem number 6. So we use our formula. We already did the dot product. We did the length of a, and there's the length of b using the components of b. Simplify and then use your calculator to do the inverse cosine of negative 11/14. Number 24. Write the equation for the sphere with center 3, negative 4, 3 that is tangent to the xz plane. Well, you know I love to draw a picture. So there's the center at 3, negative 4, 3. And if we draw a box to the xz plane, which is the plane coming out towards you, then the distance from that center to the xz plane will be the radius. So the radius is 4, and we have the center, so we just fill in our equation. X minus 3 squared plus y minus negative 4 squared plus z minus 3 squared equals the radius squared. Number 28. Find the center and radius of the sphere whose equation is 2x squared plus 2y squared plus 2z squared equals 7x plus 9y plus 11z. Well, we would need to put it in the other form. So the first thing I did was divide by 2. And the second thing I did was complain about those silly numbers. Why couldn't they have made it come out nicely? Grr. Then I brought everything to the left side. And then, yes, you guessed it, we have to complete the square 3 times. So we take half of 3.5 and square it, half of 4.5 and square it, and half of 5.5 and square it, and then add the sum of those 3 things squared to the other side, which I thought might be a nice square, but it's not. Then we factor, and so pretty obviously then our center is 1.75, 2.25, and 2.75, and our radius is the square root of the quantity on the right, which is approximately 3.961. Number 30, describe the graph of x equals 0. Well, what does this mean? This means x is always 0, but y and z can be any value. So in 3 dimensions, that is not a line. y can be anything, and z can be anything. So any point on the yz plane is part of this graph. And so basically we just get the whole plane. The graph of x equals 0 is the yz plane in 3 dimensions. 38. Describe the graph of x squared plus y squared equals 0. Well, basically what they're doing is they're telling us that x and y are always 0, but since z is not mentioned, that means z can be anything. So this time we have to stay at 0, 0 on the xy plane, but z can be anything. And so x squared plus y squared equals 0 is the equation for the z-axis. Number 42. Given vector A is 12i minus 20j plus 17k, and vector B is negative 9i plus 15j plus 24k, determine if A and B are parallel, perpendicular, or neither. Well, if A and B are parallel, then A would be a scalar multiple of B. And pretty obviously that's not working. So they're not parallel. If A and B are perpendicular, then the dot product is going to be 0. And the dot product is 12 times negative 9 plus negative 20 times 15 plus 17 times 24. And guess what? That is 0. Bingo. Therefore, A and B are perpendicular. 44. Determine if the points P, Q, and R lie on the same line. Well, there's Q. I did that one first because it was easiest. 3, 3, 3. And then there's P. And there's R. Now I realize I didn't draw these super duper to scale, so it looks like they might be on the same line. Well, if they're on the same line, then these two vectors, QP, the vector from Q to P, and the vector from P to R, if in fact those 3 points are on the same line, then those two vectors should be parallel, should be in the same direction. So let's compute QP using head minus tail, and then let's compute PR using head minus tail, using those 2 points. And sure enough, pretty obviously, PR is twice QP, and therefore these vectors are parallel, and the points P, Q, and R do lie on the same line. Number 48. Compute the angles in a triangle whose vertices are given as follows, A, B, and C. Well, you know I like a picture. So there's my picture. And what we're going to do is we're going to get vector AB by subtracting B minus A. And then we're going to figure out vector AC by subtracting C minus A. And then what we're going to do is we're going to use our handy dandy formula. Dot those two vectors together and divide by their lengths, take the inverse cosine, and turns out angle A is 90 degrees. Okay, so then we're going to do the same thing for another of the 3 angles. I chose to figure out angle B. BA by subtracting A minus B, and vector BC by subtracting C minus B. And then to figure out the angle B, we take the inverse cosine of that dot product divided by the 2 lengths, which comes out to about 68 degrees. And now that we've got 2 angles, all we have to do is subtract those angles from 180 to get angle C. Problem number 50, compute the direction angles for PQ given P and Q as these points. Didn't bother with the picture this time. To get PQ, we just subtract Q minus P. And then here are our formulas. And so for alpha, we take the cosine inverse of the dot product of V with I. When we dot V with I, we only get the first component, the I component of V, divided by the length. So angle alpha is 98 degrees. Same thing for alpha for angle beta, except this time when we dot beta with J, we get the second component of V, namely 3. And finally, gamma is cosine inverse of the third component when we dot with K divided by the length of V. And so those are the 3 directional angles. Problem number 54, compute the work given if the force is this vector and the movement is in a straight line from P to Q. Okay, first we have to get the distance vector by taking Q minus P, because we're moving from P to Q. And then for the work, we just dot the force vector with that distance vector, and we get 48. Now it's your turn to work some problems. Have fun.